Okay, well, again, thank you for having me and thank you for being here. Yeah, so this work is about thinking about fractals in terms of these category theoretic constructions. So I'll talk about the background and I'll talk about what these things are and why we care about them or why they're good ways to like collect information, and then some work that's been done so far in thinking about different fractals this way, and then the work that we did. So this is all joint work with Larry Moss at IU. Yeah, okay, so here we go. So here's some of the background. Oh no, it didn't like that. Okay, here, let me, oh, there we go. Okay, all right, so we'll be talking about algebras and coalgebras. So we're going to start with a category, which is just a collection of objects with morphisms between them, satisfying some requirements. And so if we have a functor from this category to itself, so in other words, a map that takes objects to objects and maps the morphisms accordingly, then we can define an algebra to just be an object from that category. This is A, and then a morphism in the category from FA to A. So it's so that's an F algebra, and the ones that we're particularly interested in are what we call initial algebras, which is kind of what you would expect. So this object A with this little a map from FA to A is an initial F algebra. If for every other F algebra, you can map the A one into it in a way that makes sense. So that's exactly what's depicted here. So if you have another F algebra B, then there's a unique morphism from A to B such that this diagram that's here commutes. So, and like I said, these initial algebras are going to be a cool way to capture a lot of interesting information. We'll see an example in a moment. But ultimately, what we're going to be interested in is the dual notion of this, which are coalgebras and final coalgebras. So the dual notion of an F algebra is an F coalgebra, and you can see that the direction is just reversed. So these are going to be morphisms from the category which go from your object A to F of A. Okay, and then of course a final, this is a final F coalgebra if you can map any other coalgebra into it. So it's just the same thing with everything going the other direction. And these coalgebras are going to be also a way to sort of capture information we want, but in sort of a more continuous way. And this is going to lend itself well to thinking about fractals. So these are sort of the ways to capture like data structures and different things that are relevant to us. So I'm going to give a couple of motivating examples what I mean by like capture information that we care about. Okay, so let's start with initial algebras. So let's look in the category of sets and let F be the functor which takes a set X to 1 plus X. So this is just a set that consists of all the elements of X and then one fresh new element. Okay, so that's going to be a functor on the category of sets. And then I'm going to look at the object natural numbers and define a map or morphism in this category from n plus 1 to n, where I take the new element in n plus 1, that new fresh element that we got by hitting it with this functor, to 0, and then all the n's to n plus 1. Okay, so you can see that this is just a set map, which are the morphisms in the category. Okay, and what we're going to argue is that this object n with this morphism S is going to be an initial algebra. Okay, so right out of the gate, we can see it's an algebra. It's just the right type of map for this functor. Okay, and in fact, the reason it's going to be initial algebra is because of recursion. So recursion on n, we can state it as follows: that if you have a set A and you designate some element A and A, and you have a function f from A to A, then there's a unique way to, or a unique phi from n to A, so that you designate phi of 0 as A, and then phi of n plus 1 is f of phi of n. So just defining this recursively. So saying that there is a unique map like this winds up being equivalent to saying that this thing is an initial algebra in this, an initial F algebra in this category. So here's how you can think of that. So in other words, all this information about having a set A and designating a little element A, little a and A, and a function f from A to A, you can think of that as an algebra, right? So in particular, an F algebra. So this alpha here would send the the fresh element to this little a, right? So you designate your a. And then saying that this phi exists is exactly saying that there's a unique phi which makes this diagram commute. Okay, so you can sort of check it out and make sure that this gives you, like if you look at this diagram commuting, it's exactly what we need for phi of 0 to be a and phi of n+1 to be f of phi of n. Okay, so this is sort of the intention I mean about like, or what our intention is with capturing information via initial algebras, is that by stating that this like setting up this functor and this object and this morphism and saying it's an initial algebra is equivalent to capturing this information that we care about. Okay, so like I said, we're going to be more interested in coalgebras ultimately. We're going to use some initial algebras throughout as indicated in the title. Yeah, so let me give an example of something like this with a coalgebra. And we'll see that it's sort of more continuous in nature, which you can sort of imagine would lend itself better to thinking about fractals. So let me roll through a little example for coalgebras, and then we will start talking about fractals. So here's a nice coalgebra example. So I'm gonna, again, we're still working in the category of sets, and we have the same functor, this +1, we're adding a fresh element. Okay, and then we're gonna take the object to be n with an infinity element. Okay, so our object n is the natural numbers and this infinity. And then I'm going to define S from n to n+1, because remember it has to go the other way for coalgebra, to take 0 to this fresh element. And then I'll take x+1 down to x for x greater than 0, and then take infinity to infinity. And I use the star to denote the fresh element that's given to us by applying this functor. Okay, then here's what we can do for, whoops, oh no, I clicked away and now, okay. Sorry. A coalgebra, like, so what I'm going to do is I'm going to explain why this is a final coalgebra. So what I need to do is sort of explain how it is that coalgebras are going to map into it in this unique way. So let's look at a coalgebra, an F coalgebra in this setting. So how can we think of it? Well, an F coalgebra is going to consist of some map from A to A+1. And the way that we can view it is we can think of it as giving streams of elements from A. So the idea is that if I take like some X in A, I can consider like X, A of X, A of X, etc. as like a stream of elements. And either it's going to terminate if after some finite number of steps, your AN of X is going to go to that fresh element because that's not an A, so you can't keep applying A to it, or it's just going to go on infinitely. Okay, so this is going to kind of capture sort of streams of elements of A. Okay, and so it turns out that we can uniquely determine a map from A to N in the following way. So if X is the start of an infinite stream, then we'll let f of X go to infinity. And if this is the case, then this f+1 of A of X is also going to go infinity because A of X will still be the start of an infinite stream. Okay, and then otherwise, we want to send it kind of to the length of the stream. Okay, so otherwise, if X is the start of a stream of length n, f of X is going to go to n, and then f+1 of A of X, well, what is that going to be? That's just going to be f of A of X is going to be n-1 until you get all the way down to your star, right? So f+1 of A of n of X is going to be f+1 of the star, that fresh element, which is just going to go to this star. Yeah. Okay. So all right. So then here's the, oh man, I keep clicking away. All right. So here's the punchline, is that this unique morphism is what's going to make this diagram commute. So again, this is a way to think about this thing as a final coalgebra. Now it's not as explicit how this is sort of capturing a thing as the example with the sort of definition by recursion, but the point is that we're looking at some like collection of information that we're capturing by way of relating it to this this final coalgebra via some unique maps into it. Okay, so what we're going to do with fractals is we're going to set up a situation in which we can take an object which is ultimately what we're going to want is Bilipschitz equivalent to a fractal. So we're going to work in metric spaces, but an object which looks like a fractal we care about and show that it occurs as a final coalgebra in an appropriately chosen category. Okay, so that's what's up. So let's start by talking about some of the work that's been done towards this. So I'm going to start with Freyd's theorem, which is about the category of bipointed sets. So basically what we're going to be doing is looking at unit intervals and kind of gluing them to each other and iterating through this. So let me describe the situation and then talk about how to think about it. So bipointed sets are just where you have a set X and then you designate some distinct elements, which are the top and bottom of the set. So again, the intuitive way to think about this is that think about like the unit interval with like 0 and 1 as the bottom and the top. Okay, so take the category of all those guys. And then we're going to define a functor in the following way. So we're going to take M, and the way you can think about M is it's kind of an index set. And in this case, it's just going to mean left and right for bipointed set X. And then let M tensor X be just the pairs of elements of M and X, modulo identifying the top of the left and the bottom of the right. So the idea is that you take your X, and then you're going to take two copies of it indexed by left and right, and then you're going to glue them together at the top of the left and the bottom of the right. Okay, and then you have to designate the new top and bottom. So the new bottom will just be the bottom of the left, and the new top will be the top of the right. Okay, so this will give you another bipointed set. And the point is that we can, so like if we think about in particular, like let's look at the unit interval, the example I keep giving. So we can define I of X to be left 2 times X when X is less than half, and right of 1 minus 2X when X is greater than 1/2. So that's going to map 0, 1 into this M tensor X. And that's going to be a morphism. You'll see that it preserves the designated points, the bottom and the top. Okay. And then so here's Freyd's theorem is that this thing is in fact a final coalgebra for this functor from bipointed sets to itself. Okay, so this is kind of a good like motivating example of what the kind of construction we're going to want to like think about other fractals, and we'll see more examples in a bit. So the way that we prove this, or a proof of this, so this is not the original proof of this, but a way to think about the proof of this thing being a final coalgebra is the following. So the idea is that, again, for any, that should say coalgebra, sorry, for any coalgebra from X to M tensor X, we need a unique morphism which makes this diagram commute. So what we can do is we can use this map phi, which is going to map, it's going to be a map on the collection of morphisms from X to I. Okay, so it takes F from X to I and maps it to this composition here. And we see that that's that the set of morphisms from X to I is going to be a complete metric space. Okay, and this phi is going to be a contractive map. So what we can do is we can get a unique fixed point for this phi map. Okay, so and the unique fixed point of that is exactly going to be the F that's going to make this diagram commute. Okay, so this is sort of a technique we'll see throughout for finding unique maps that make the diagrams commute to show that things are final coalgebras. Okay, so that's sort of a start to this work, and then to build upon this, Moss et al. Developed a framework to understand these fractals in categories of metric spaces. So a natural sort of notice this occurred in a category of sets, right? So we want to consider these things as metric spaces. So in their paper, they considered, ultimately it was towards understanding a way to view the Sierpinski gasket as a final coalgebra. So we review the results in there, and it kind of gives us a roadmap of what we're going to do for the Sierpinski carpet. So, okay, so tripointed metric spaces. spaces. So we're going to transition our study to a category of metric spaces, which makes sense because fractals are, we often want to view them in the context of a metric space that they live in. So we're going to define tripointed metric spaces as follows. It's going to be a metric space bounded by 1, and you have 3 distinguished elements. And ultimately, these are going to lead to a triangle. So you have a top, left, and right, and we designate them as pairwise, 1 apart from each other. Okay, and then so we take this category of these guys, and the morphisms are going to be short maps, which preserve the top, left, and right. So short maps are just going to be non-increasing maps, and then we need to preserve the designated points. Okay, so that's the category that we're going to work in to think about triangles. So some examples. Well, okay, this is a few iterations of a Sierpinski triangle. That's kind of what we're headed towards studying. Something like just the top, left, and right, that's going to be an initial object because that'll always map into any of the objects in there. Turns out there's no final object, and the way you can conceptualize that is you can think of something like the initial object with like 1 extra point in the middle that's designated to be like 1 away from everything, and that's not gonna, you're not gonna be able to uniquely map that into any supposed final object. Okay, so there's more than one way to send that middle point around to the corners. Okay, so yeah, so what we want to do is define a functor on this category, which when the intuition is that we want to define this functor so that when we apply it infinitely many times, that we get something that's like this Sierpinski gasket, this triangle. So we're going to let M be, remember in the bipointed set example, M was kind of like an index set. It was like saying, you know, where you're going to put copies of your thing. So now I'm going to let M be A, B, and C, okay? Because like you can see in this little picture here, it's like you take a triangle and then you shrink it down and put 3 of them on the top, left, and right, and then you keep doing this. So that's going to be sort of our index set of where to place stuff. And then we define a functor which takes tripointed sets to this M tensor X, where it's just pairs modulo the equivalence where A of the left is B of the top. So if you think of A, B, C as going counterclockwise, starting on the top, you're identifying like the bottom left corner of the top triangle with the top right of the left triangle, etc. So it's just sticking them together exactly how you would expect. Then this is a tripointed set, tripointed set via identifying the top with the top of the top one, the left is the left of the left one, and the right is the right of the right one. So so far we have that it's still it's a tripointed set, but we need to think carefully about how to define a metric on this new M tensor X. Okay. Yeah. So far this is exactly analogous to what was going on with bipointed sets. We got tripointed sets. Okay. So now we need to discuss how to describe a metric on this thing. So here's how we're going to do it. We're going to do something called the quotient metric. And the idea is that, so if you think of these as your 3 copies of X, and I have kind of the equal stuff like lined up. So like the A left is that double line is that it's identified with B top, etc. So the quotient metric that we're going to define on this thing, so given like 2 points in M tensor X, the distance between them is going to be the inf of all the scores of the finite paths. So what that means is we take like a finite path through this thing of points and then add up their distances. So here's how that's going to work is that if 2 of your points in your path live in the same copy, so one of these teardrop shapes, then they're scaled by 1/2. So it's just 1/2 the distance that they would be in the original X. And if they're identified like A left and B top, then the distance between those is 0. And otherwise, if they're not identified, then they're going to be the max distance 1 apart from each other. So the point is that you should be able to, this is connected, right? So you should be able to take like any 2 points in here, you should be able to cook up a path that walks along these identified points such that you get some, such that you can add them up to get the distance. So you take the inf across all of these paths. Now, as this is given, it's definitely going to be symmetric and satisfy the triangle inequality because you can just concatenate paths. But it's not automatically a metric. It's a pseudometric right out of the gate because it's the inf of a bunch of paths. So we don't know automatically that this thing is going to be a metric. But in their paper, they gave sort of explicit descriptions of what the distances are going to be, and it turns out it is a metric by way of this sort of like explicit view of what these distances are. So in this case, it does work out to be metric, so that's good. Okay, all right, so we've got this metric on this thing. So then let's sort of summarize the results, and this is going to give us kind of a roadmap of what we're going to do in a moment with the Sierpinski carpet, which is the square. So here's what they did. So they started, now it's in the title that we view it as a coalgebra by completing an initial algebra. So this is going to be one of the advantages of working in metric spaces, is that, okay, so we start with the initial object, this TLR, and then look at this initial chain. So remember sort of the intuition I said is that we want our M tensor functor to kind of be such that when we apply it a bunch of times, we get sort of iterations of this fractal we care about. So we're going to look at this chain of isometric embeddings, and we can use that to get. Sorry, because this is a chain of isometric embeddings, it has a colimit. So in other words, it has some object that all these guys map into that has some nice universal properties, and from that, and in particular, that colimit is going to be preserved by the functor. So M tensor G is going to be isomorphic to G. Okay, so that's a good thing, because what that's going to let us do is use Adamic's theorem to get an initial algebra with this G that occurred as this colimit. And I'll actually state Adamic's theorem in a little bit because I'm going to use it for my stuff. But just that results from this thing being a colimit. Okay, so those are kind of ingredients that we're going to want. And then what they do is they take the Cauchy completion of G and they flip that map around. So you get this thing is an isomorphism, this G, so you can swap it and get a map from the Cauchy completion to M tensor the Cauchy completion. And then you can argue that this is a final coalgebra by a similar argument to that fixed point thing we saw for Freyd's theorem. Okay, so this is sort of the, let's see, is that, oh, and then at the end of the whole thing, what we're gonna, like, so how is this the Sierpinski gasket? We're gonna show it's Bilipschitz equivalent to the Sierpinski gasket. Okay, so this is sort of the outline of what this new work is following towards understanding how to sort of generalize this. So all this work was done specifically in the context of Sierpinski gaskets, or the triangles. So a question I had was, what about fractals that we can view as like gluing copies on different sets, so not just at points? So let me put up a picture. Yeah, okay. And this thing made the tech file take like a jillion years to render. So, okay, so the Sierpinski gasket or triangle, I've got a few iterations here. And you can see that one way you can conceptualize what's going on as you're iterating through it is it's like you take this first triangle on the left here, and then you scale it down by half, and then you take 3 copies of it and glue them together at these points, right? So at the bottom left, the top one to the top of the left one, etc. Okay, and then you can think of repeating this process. So then take that one, shrink it by half, glue them at the points, and then keep going indefinitely. So another very similar fractal of interest is the Sierpinski carpet, which is where you kind of just do the same thing with squares. So a way that you can conceptualize the iterations of the Sierpinski carpet is by you take your square and then you shrink it down to a third, and then you glue them together along segments. So like the bottom segment of the top square glues to the top segment of this middle square, and then the bottom segment of that glues to the top segment of the bottom square, etc. So this winds up being kind of a noteworthy difference in how it's constructed, and it's going to require somewhat substantially different approach for like filling in the gaps in that sort of roadmap I put up on the previous slide, because it's not going to behave as nicely. So understanding the quotient metric in this context of like gluing across segments is going to be a little tougher. And you can sort of intuitively see why, because there's not, you know, they were able to get like a really explicit description of the for the triangle, because all the paths just go, there's only so many points to go through. So that's kind of a way to think about it. Whereas if you're walking through a segment, you don't know where you go through. So that's kind of something we're going to have to address. Okay, so I'll point out those differences as we get to them. Okay, so the goal here now is to set up a category and a functor so that we can get an object which occurs as a final coalgebra and is Bilipschitz equivalent to the Sierpinski carpet. So that's the goal. Okay, so here we go. Let's do it. Okay, so we're going to define an analogous category of square metric spaces. But now already our designated set is going to be more complicated than just like the 3 points. So we're going to need the entire boundary of the square. And again, intuitively, it's because those are like the sets that we need to glue the copies together on. So I'm going to let M0 denote just the boundary of the unit square, which I have there, and say that a square set is a set X with an injective map from that M0 to X. So just a map which designates the boundary of your square set. Okay. And then we say it's a square metric space if it's a metric space bounded by 2, and we'll see why we use 2 in a moment, and such that you have some sort of requirements on how distances behave on the boundary. So in particular, on your boundary square, along one side, you should have your distances should coincide with the unit interval. So if you live on the same side of the square, then that distance should be like, if you're looking at a point like Sx of S0 and Sx of R0, like you're along the bottom, then that distance should just be like the absolute value of R minus S. Okay, so you want your sides to behave like unit intervals. And then you have some non-degenerate requirements. So points on opposite sides need to be at least 1 apart from each other. And corners need to not collapse. So what that means for the corners is just this technical requirement that like if you're looking at points on adjacent sides, that their distance is greater than or equal to the max of the distance from each of those to the corner. So you can't think of your corners as like smushing down. So this is just like technical requirements to make this thing work. Okay. And then so some examples of some square metric spaces are, well, you can think of just that boundary with the identity map as your boundary. And in fact, this thing is going to be an initial object because it's going to uniquely map into all of them via that SX. So that's cool. Or this is kind of a noteworthy example because we're going to use it a bunch, but take the solid unit square, okay, and then let the metric be the max metric. So the way that's going to be defined is it's the max of like a horizontal component and a vertical component. So it's like the max of x0 minus x1 and y0 minus y1. And we're going to see that that's going to be like a really useful thing. Ultimately, that's what we're going to use to get the Bilipschitz result. So it's a thing. Okay. And then, so square metric spaces is going to be the category whose objects are these square metric spaces. And then the morphisms are going to be short maps, again, just non-increasing maps, which preserve the boundaries. Okay, right, so far it's basically analogous. It's just our designated points had to be kind of special. And instead of just saying like, oh, they're 3 points and they're all pairwise 1 apart from each other, we had to describe this in more detail. All right, so what are we going to do with this? Well, we want to make our carpet. So our index set M is going to be just the 0, 1, 2 squared without the middle, because we want to leave out the middle every time. Okay, and then we can define, so here's how we get the quotient metric. We define a metric on M times X just to be scaled by 1/3 if you're in the same copy, and then the max distance 2 otherwise. Okay, and then we define our quotient metric. So this is just saying like within copies, you're scaled by 1/3. So the quotient metric is going to be this. So actually writing this out in detail is very long, but It's kind of exactly what you would expect. So it's the same thing we do in tripointed metric spaces, where we take the inf across all the possible scores between 2 points, and where we identify points along those segments that I've put the little squigglies between. Okay, so what we want to do is find the inf of all the paths of the ways that we can walk around this this thing through identified points. Okay, so what I wanted to do here is I wanted to give a more general argument about quotient metrics. So I have the following proposition. It's going to look kind of scary, but so the metric, like we talked about with tripointed metric spaces, the quotient metric, just like given as it is a pseudometric since these distances are infs. So yeah, okay. So what I wanted to do was like kind of collect relevant information that we needed to make sure that this quotient metric was actually a metric. So this is kind of a lot of writing for just saying that like you need a few things. So you're working in a category of metric spaces that are all bounded by some n, and then such that you have some additional structure designated by SX, like we did in the square spaces, such that that image is compact, which it is for the square metric spaces. And the morphisms need to be short maps. And then you need M to be a finite index set, and your equivalence relation identifying points needs to only depend on M and M0. And then you have a few other requirements that this identification is sort of isometric and closed, and that you can have this SM tensor X, that there's a way to identify the boundary of your new object. So if you have all of that, and then I put in blue, this is a biggie, and we'll talk more about that in a second. And you know that when you go into the quotient metric, that the shortest distance between points in the same copy is just their distance in that copy scaled by whatever your scaling factor is. In this case, it's 1/3. Then your, oops, oh no, come back. Okay, then your distance is actually witnessed by a specific finite path, which tells you that the quotient metric is in fact a metric. Okay, so this is a long list of requirements, but they're all reasonably natural except for the one in blue, which we have to carefully check. Okay, so like I'll note that like in tripoint metric spaces and other fractals that are just glued at points, all these requirements are satisfied almost immediately. Stuff like that the image of M0 is compact. Well, yeah, if it's just 3 points, then it's a finite number of points. Of course, it's going to be compact. Okay, so like these requirements are easily satisfied by the examples with points. And it turns out they're also satisfied pretty readily by our square metric spaces. So I do ask a question like, what's a broader class of fractals that maybe are satisfied this stuff? Okay, but so like I said, the one in blue, the thing about that you can't like go outside of a copy of X to get a shorter path. This one is a little tougher to prove. So for square metric spaces, we use the following approach, which is what we call the region contact graph. So if you look at, let me go a couple slides back. Okay, if you look at the setup like M cross X or ultimately M tensor X, you can view paths between, so say you're working in one of these squares, a path between these points, you have to walk through adjacent squares, right? Because if you skip over one, then you just reach the max, the max distance. So we can capture that via a graph. Okay, so these are kind of like the places you could go in your path. And then we can argue that if you're looking at 2 points in the same copy of X, well, that's going to correspond to a cycle in this path. And then you can examine the cycles and prove this by induction that you get the result. So yeah, I pose a question is like, can we rephrase this requirement in terms of like a property of this graph, and what are some other fractals that we can apply this to? Because this is not the argument that was used in the tripointed metric space one. They gave a explicit description of the metric. So yeah, this is something I would like to further generalize if possible. Okay, so now we know the quotient metric's a metric. So now we know that this M tensor is a functor. Okay, so that's a good start for getting algebras and coalgebras. All right, how are you? Okay, good. All right, so then as far as algebras go, okay, so I just want to give an example of a class of algebras in square metric spaces. And this is the one where, this is the example I gave on the slide where I defined them. So I'm going to let U0 denote the unit square, the solid unit square, and then take the max metric on that. So that's this thing where you take the max of the horizontal and vertical distances. And then you can define alpha 0 from m tensor U0 to U0 the following way is sort of 1/3 of the addresses here. And a way you can intuitively think about it is it's just like pasting this one iteration onto the unit square itself. Okay, so it takes this, if you plant that on a coordinate axes, that's what it's going to give you. Okay, so you can argue that this thing is in fact a short map, and the intuition for why it would be a short map is that when you go up to m tensor U0, you have to walk around that hole in the middle. Okay, so whereas then you drop down to the solid square, you can go through it. Okay, so the point is that our morphisms all need to be short maps. So as you iterate through this, each one of these arrows is going to be a morphism in the category because like in a higher iteration, there's more holes that you have to walk around, whereas in the previous iteration, you can go through them. So that's the idea. So we get a class of m tensor algebras, okay? And I'm going to use this in a little while, so that's why I bring this up. But and these are injective short maps. That's what I just said. Okay, and then one nice thing about this is it does kind of give us a geometric view of how this thing looks like iterations of the Sierpinski carpet. So this is kind of a good sort of anchor for where we're trying to go with this. Okay, so keep that one on ice for a moment while I give you this mess. Okay, all right, so let me talk about an object G. So if you'll recall from my little roadmap slide, what they did was they took G to be the co-limit of this sequence of initial, where you start with the initial object and you apply the functor. Okay, so that's the second line. I don't know if you guys can see my cursor. Can you guys see that? Yeah. Okay, so that's the second line here. And so in the tripoint metric space example, that was those were isometric embeddings, which allowed them to just get the co-limit, like to show that that thing exists. But here's the problem in this case is that these are not isometric embeddings. The distances can go down as you iterate across this. So you don't get this co-limit for free. So here's how we got around that. Here's how I thought about it, is that I took this G to be kind of what the set co-limit would be. So a way you can think about it is it's all the sort of finite addresses from M and M0. Okay, so like it's sort of like another way you can think about it is it's like a disjoint union of this chain. Okay, up to some equivalence via applying these maps. So here's the thing though, is that we don't know for sure that that thing is a metric space. So you can define a metric on it to be like, if you take objects in G, then they have to live in some MN, okay? And then what I want to do is say like, okay, let's define the distance in G to be the inf of the distances as you go along this chain. Okay, so that should make sense because the distances go down as you move across the chain because they're short maps. Okay, but the issue is, again, this is a pseudometric because you're taking an inf, so distinct stuff could go down to 0. So the way you get around that is the top part of this chain, the U0s, and you say, okay, look, actually what you can do then is you can look at these XP, YPs, so those live in some like MNP tensor M0, and you can go up to the U0s and then over all the way down to U0 itself. And because these maps are all injective, if you start with distinct stuff, then you're going to go to distinct stuff in U0, and then those are going to be some positive distance. And then as you iterate across, those all go to the same place because this diagram commutes. So that's how you get distinct things bounded below by a positive distance. So this was a notable departure from what happened in the triangle case because we had to think about how to get this G to be a metric space. So that's a thing. Okay, so there's our co-limit. Now we can view G as a co-limit of this thing. And then we also had to show directly that M tensor G was isomorphic to G. That's just it's a routine argument. So now we can apply Adomic's theorem to get that this is an initial algebra. So here's the theorem. I mentioned it once already. But it's basically saying if you have this exact situation, then this thing is an initial algebra. So you've got a co-limit of an initial chain, which is preserved by the functor. then that thing is an initial algebra. So far we've got G to be an initial algebra. So that's a good start. Okay, then the next maneuver in the triangle case was to take the completion of this and argue that that thing is a coalgebra, final coalgebra. So we're going to make that move here, and I'm just going to talk about it in a little more detail. This part behaved exactly the same as the triangle case. So the way you can think about it is, look, you've got your isomorphism, so you can swap the direction, and then take a functor which takes objects to their Cauchy completions. And what you can do is you can show that that functor commutes with the M tensor functor. So you move the completion inside of M. So the point is that you get a composition of maps from the completion of G to M tensor the completion of G. And we'll just let Q be that thing and let mu be the map from Q to M tensor Q. So again, this move is like really the same as what they did for triangles. But then to argue, now we need to argue that this thing is going to be our final coalgebra. Okay, so yeah, this is pretty routine. There's a little bit of work to do for beta and gamma and making sure that those things are natural isomorphisms, but just that they preserve the square set structure, which they do. So that's good. Okay, so this is the object we're going to work with now. It's going to be the completion of this G to M tensor that, and we're going to show that that's a final coalgebra. So here's the big punchline here. So this is the theorem we're going to use to show it. Now this is new and kind of a more general reformulation of the approach they took in the triangle paper. So this first assumption is that we have a short enriched category. I'll talk more about that in a moment, but basically we get this for free as long as our maps are short maps, but it's somewhat more general, maybe. Okay, and then we have a contracting endofunctor and a coalgebra. Then as long as the map in the coalgebra is invertible, and that for every other coalgebra you have some map from B to C, and that's a complete set, that then this thing is going to be a final coalgebra. So we want to apply this to the thing we just defined, and we get most of this for free. We get short enriched because your stuff is, our morphisms are short maps. This thing is going to be a contracting endofunctor. We can just show that directly. And our map is going to be invertible because we got it as an inverse of a thing. Okay, then the main thing we have to show in blue is that given a coalgebra, that there's just a map from B to C. Okay, then this theorem shows that that's sufficient to get the final coalgebra. And the proof of this theorem uses that same fixed point type argument. But you have to start this set needs to be non-empty to apply that fixed point thing. So, and you get the completion because Q is going to be complete. So we get that sort of for free. So this blue part is the sort of main thing we need to do to be able to apply this theorem to get that our thing is a final coalgebra. And I'll just throw this up here. Like I said, this short enriched is meant to be a generalization. Not totally sure if this is actually a generalization. Because the idea here is that if you look at the statement of this theorem, it doesn't actually require that the objects be metric spaces. It requires a metric on the Hom sets. So, but I'm not totally sure if it induces a metric on the objects. So if there's an object with a single point, then it does, because you can just take the Hom set from that to the other stuff, to the other objects. But so I don't know about that yet, but in any case, this is what we're going to apply. And the last thing we need to do is prove this blue thing. So here's how we're going to do that. And that's it's kind of a beast. So we have an intermediate result, which is that Q occurs as a limit of this chain. So what that means is that we have maps from each of these, from Q to each of the things in this chain. And then we have this sort of universal property that if we have another object with those maps, that there has to be a map from that object to Q. So see how that's already going to kind of lend itself to what we want to prove, that if we start with a coalgebra B, that we have a map to Q. So here's how we're going to do it. What I'm going to do is start with a coalgebra B. Oh yeah, so this is what it means for Q to be a limit, that if you have some B hat with what we call a cone, so maps from B hat to all the things in this chain, then there is a unique morphism, that should be singular, from B hat to Q. Okay, so here's how we're going to do it. We're going to take a coalgebra, okay? And then this requires a little bit of work, but we can find B hat to be the co-limit of this chain here, such that M tensor B hat is isomorphic to B hat. And the way this is going to work is basically what you do is you take the disjoint union of this chain, and then you have to mod out by images along the chain, and then you also have to mod out by like distance zero stuff. Because remember, when we showed G was a metric space, we had to like navigate up to U0 to show that it wasn't a pseudometric. Here we don't have that, so we're just going to mod out by the distance zero stuff. Okay, so we can cook up this thing. So what we're gonna do then is get a cone from this B hat into this thing, and that will give us a morphism from B hat to Q. And because B hat is the colimit of this chain, we have a morphism from B to B hat. So we're going to compose those. So this B hat is just kind of like an intermediate step towards a map to Q. Okay. So, and we'll talk about the reason why we don't just go directly from, well, I'll say that right now. The reason we can't just go directly from B to Q is we don't really have any information about B other than that it lives in a coalgebra. So like to try to define a map directly from B to Q, like you have nothing to work with. So the reason I use this sort of auxiliary B hat is that because it occurs as the colimit of this chain, you get something that looks kind of like that G we dealt with, where you have like all the sort of finite lists of addresses from M then anchored in a point B. Okay, so that's sort of the intention here. So, okay, so yeah, there's morphism from B to B hat. So what we need to do is get from B hat to all of these elements of this chain. So here's how we're going to do it. Are we almost out of time? Okay, yeah, we can get through this. Okay, here we go. So every element of B hat is going to be associated with an infinite list of addresses from M. And again, the idea is that B hat is kind of like the disjoint union of all of these Mn tensor Bs modulo some equivalent stuff. So the point is that I can define a map from B hat to U0. Don't worry, we're getting to the chain in a sec. As sort of this sum of these things, okay? And it requires a fair bit of work to show that this thing is in fact a morphism, that's a short map, that it preserves the edges, but it does. And sort of intuitively, again, this is analogous to those alpha maps where we took copies of U0, like M tensor U0 into U0. So this requires some technical work, but it does work out. And then we get our cone because M tensor B hat is isomorphic to B hat. So now if I have this F as a morphism, I can just hit it with M. And what I get are morphisms from B hat to Mn tensor U0, because they're really from Mn tensor B hat to Mn tensor U0, but that thing's isomorphic to B hat because Mn preserves B hat. So, or M does, so Mn does for all N. Okay, so this hitting this map with these M's gives us the cone that we need. So in other words, what we get, because Q is a limit, is we get a morphism from B hat to Q. So putting that all together, what we get is a morphism from B to Q. So this Hom set is non-empty, which is what we needed. So there's the theorem. Okay. All right. So I have like one more thing to say, and I have about 1 minute, so that's perfect. Okay. All right. We got our completion as a coalgebra. And again, this is kind of a departure from what they had to do in the triangle case, just because these distances aren't as nice. Okay, so yeah, the main sort of auxiliary result that we used was Q being the limit of this chain, which the triangle stuff doesn't have any results like that. Okay, so then here's the punchline, is that this Q, which we have now expressed as a final coalgebra, is Bilipschitz equivalent to some view of the Sierpinski carpet. So this is kind of a dense slide. I'm just going to kind of say what's going on here. So you take your Sierpinski carpet and you first show that it's Bilipschitz equivalent to considering it. So you take your Sierpinski carpet just in the plane with the Euclidean metric, and then show that that's Bilipschitz equivalent to that thing with the max metric, that one that I keep talking about, how you just take the horizontal and vertical components. Okay. And then you can argue that the max metric is Bilipschitz equivalent to the metric on Q. So this bottom line of the slide is the important part. So like, here's an example. So if I look at via the max metric of the point 0, 1/2, and 1, 1/2. So it's like the bottom middle and the top middle. Those are going to be distance 1 via the max metric or even the Euclidean metric. Okay, but in DQ, well, the idea is that for each we can approximate it with iterations through like mn tensor m0. So each time you iterate, you add a new hole that you have to walk around. Okay, so and then every time you add a hole to walk around, it's a factor of like 2/3 to the n. So down here at the bottom, we have the summation of the stuff we add. After all the iterations, we wind up adding 1. So this is how you argue that via a factor of 2 that you get the inequality that you need. Okay, so that's a really rough statement of how this like several page argument goes to show this Bilipschitz equivalence. Okay, so that was yeah, so that's the result. And I guess that's it. So thank you.